Welcome back. After having the mathematical foundation for Laplace transform, we can finally use Laplace transform for what we motivated to do, which is to solve ordinary differential equations. In these sections, we will demonstrate some examples of solving ODEs with Laplace transforms. First, let us recap what Laplace transform can do for solving complex ordinary differential equations. So if we have a difficult ODE to solve, and we want its solution, getting it there directly might be very complicated and difficult, because you need to solve for a general solution and a particular solution if it's non-homogeneous. But Laplace transform provides us a new way to transform the difficult ODE in the real space, call it real world space, or the time domain, to the Laplace domain, or the S domain. So now we have an easy algebraic expression. In solving an algebraic problem is easier than solving an ordinary differential equation. So you get the solution of the algebraic equation, and then we perform inverse Laplace transform to get the solution of the original ODE. So this again is like thermodynamics, where the original path is difficult. So we seek an alternative path that is easier. And the Laplace transform part is tabulated. And the inverse Laplace transform is also tabulated. That part should be easy. And the algebraic part is a little bit convoluted because we want to write expression in terms of tabulated inverse Laplace transform. And usually we need to use partial fractions, which you have seen in previous videos. So let us do an example for a first-order linear ordinary differential equation with an initial value. So again, we have an ODE. We want to get its solution. It's hard, so we do the Laplace transform of it. Comes algebra. We get the solution of the algebra. Then inverse Laplace transform it to the solution of the ODE. Let us number this. Call it first step, Laplace transform. Second step, solve the algebra. The third step, inverse Laplace transform. First step is to Laplace transform the both sides of the equation. So on the left, we can use the linearity property. So we have the Laplace transform of the derivative plus 3 Laplace transform of y equals to 13 Laplace transform sine of 2t. And the Laplace transform of the derivative is s y of s minus the initial condition plus 3 y of s, and then 13 times the Laplace transform of sine of 2t. And now we need the help of the table. The table gives us that the Laplace transform of sine of at is equal to a divided by s squared plus a squared. So that in our case, a equals to 2. So we have 2 divided by s squared plus 2 squared, which is 4. And then we can substitute things in. We have y of s, we have a factor of s and 3 minus the initial condition, which is given y of 0 equals 6, so minus 6 equals to 13 multiplied by 2, 26 divided by s squared plus 4. And we can rearrange the expression to solve for y of s. So y of s is equal to 26 divided by s squared plus 4 plus 6 divided by s plus 3. And we can simplify that. 26 multiplied by divided by s squared plus 4 times s plus 3 first term plus the second term 6 divided by s. Okay, now we have gotten our algebraic. Now we enters the second stage where we solve the algebraic problem so that we can use the tabulated data or expressions to inverse Laplace transform y of s, and currently in this form we cannot do that. The second term we can inverse Laplace transform that, but the first term can't. We need to perform some algebraic manipulation in order to make it work. So what we want to do is, as before, use partial fraction expansion. In this case, we see that there is an s squared term bottom, and we cannot further expand this s squared because it has s squared plus 4. If we set it to 0, we will have imaginary. So in this case, we'll assume that if we can separate the denominators, the s squared term will carry s factor at the top, constant, and the s term will only have constant top. And this will be the expression for partial fraction. Now, as before, we multiply top and bottom, same thing, get a common denominator. 3 plus, in term we have s squared plus 4. So now we have a common denominator. And everything at the top, we can write it as as plus b multiplied by s plus 3. Let us multiply them out. We have as squared plus as 3, which is 3as. And we have bs, and we have 3b plus ds squared plus 4c. And then we see that the denominators are the same. So we can equate the numerator. 26 equals to, let us extract the coefficients. We have second order, first order, and constants. Second order, we have a and c plus c. For s, we have 3a plus b. And for constant, we have 3b plus c. And then let's match the terms. We only have a constant on the left, so higher order terms equals 0. Constant term equals 26. And that gives us a system of linear equations to solve for a, b, and c. From first equation, we have a equals to minus c, and plug it into the second, we have negative 3c plus b, 0, so b equals to 3c. And substitute that in third equation, we have 9c plus 4c equals to 26c, 26. So we have 13c equals to 26 and c equals to. Therefore, plug it back in, we have b equals to. Then also plug it back in, we have a equals to negative. And we have solved the partial fraction expansion here. So we want to plug this in so that a is negative 2s plus b is 6. C is 2. Now we have done the algebraic problem. We will substitute this part in and then perform inverse Laplace transform. Now we can do the third stage. Find the inverse Laplace transform of y of s, which already we have found the partial fraction expansion for the first one, and we also add on the partial fraction expansion of the second one. And to further simplify this, we can group the last two terms divided by 8s plus. Okay, and to find the original y of t, perform inverse Laplace transform of y of s, which is the inverse Laplace transform using the linearity property. We have negative 2s plus 6 divided by s squared plus 4 plus the inverse Laplace transform of 1 over s plus 3 multiplied by 8, which is a constant. Well, the first term looks like there's nothing in the table, so we need to further simplify it with term-wise division. So because in the numerator we have addition terms, we can expand them out. Now we have 3 terms. Then we also want to change this part. So the Laplace transform, inverse Laplace transform of y of s equal to negative 2 inverse Laplace of s divided by s squared plus 4 plus 6 inverse Laplace s squared plus 4 and plus 8 inverse Laplace. Now we can use the tables where we have the inverse Laplace transform of s divided by s squared plus a squared is equal to cosine of t. That gives us negative 2 cosine a is equal to 2t. 6, the Laplace inverse Laplace transform of 1 over s, a over s squared plus a squared is equal to sine of 8. And in our case, we have a squared equals to 4, and a has to be 2. But in the numerator, we have 1. So we want to do a trick by multiplying the top and bottom by the same thing. So we can multiply the top and bottom by 2. Multiply by 2 changes nothing. So this part gives us inverse Laplace transform sine of, and the bottom part is constant. They can be taken. Plus 8, the inverse Laplace transform of 1 over s plus a is equal to e to the negative 8. And in our case, a equals to 3. So we have e to the negative 3t. This is our final answer for the solved ordinary differential equation. And I want to highlight that although we have done partial fraction expansion, which is tedious, but it would be far worse to solve the original differential equation because we have an non-homogeneous term. So we will have to solve a general solution. And then we have to solve a particular solution and add them together. And that's far more work than doing algebraic work for partial fractions. Now let us do a second order example. And to solve this, we would take the Laplace transform of the ODE, both sides as the first part. We'll have the Laplace transform of second derivative minus 3 Laplace transform first derivative plus 2 Laplace transform y equals to the Laplace transform e to the negative 4. The Laplace transform of the second derivative would be s squared big Y of s minus s first initial condition minus first derivative minus 3 times the Laplace transform of first derivative as the condition plus 2 Y of s. The Laplace transform for e to the negative at is 1 over s a. So here we have a equals to 4. So the Laplace transform is 1 over. Then we substitute the initial conditions in. So we have s square y of s minus s times 1 s minus 5 minus 3s y of s minus is plus 3 times 1 is 3 plus 2 y of s. And we group y of s squared minus 3s plus 2 is grouped together minus s, and the constant term minus 5 plus 3 is minus. Now we can solve for y of s. We have 1 over s plus 4 plus s plus 2 divided by whole quadratic term. Notice that the quadratic term can be written or factored out so that we have minus 1 and minus 2. We can verify this by multiplying these two together. We have 2, it's good. And we have minus 1 and minus 2, which is minus 3. That checks out. So the first term would be 1 over s plus 4 times the quadratic term, which we can factor out, plus the quadratic term that we can factor out, and we want to merge them together so we can multiply the last term by 1. So at the top and bottom we have s plus 4. Y of s 2. Common denominator, and at the top we have 1 plus s squared plus 4s plus 2s is 6s plus 6. 6 plus 1 is 7. Right, so we have solved or transformed the ODE to an algebraic problem. Now we need to do partial fraction expansion in order to get the algebra in terms of the tabulated expression for the inverse Laplace. Okay, so correction to the last slide, we made the algebraic mistake by multiplying 2 times 4s, 6, 8. So we have 9 here instead of 7. So now we have r at the second step to solve the algebraic problem because we want to make it partial fraction expansion. Let us write out the partial fraction expansion. for, notice that we have linear denominator, which is great for us to use the cover-up method. Okay, so to do that, let us first form a cover-up for the first term, so that we want to cover up s plus 4, so we set it to 0, we evaluate s equals to -4. First constant is equal to 9 plus s4 squared plus 6 s4 divided by, cover-up term is ignored, and -4 minus 1, -4 minus 9 plus 16 plus minus 24 divided by -5 minus 6. So we have 30 and 1. Now let's cover up the second term. So we want s minus 1 equals to 0, so s is b equals to 9 plus 1 squared, 1 plus 6 times 1, divided by, second term is covered up, so the first term 1 plus 4, and the third term 1 minus 2. That equals to 16 divided by -5. Then cover up the third term, we want s minus 2 equals to 0, so s 2. b equals to 9 plus squared plus 6 times 2 divided by, first and second term survive, so 2 plus 4, 2 minus 1. 9 plus 4 plus 12 divided by, that gives us 25 divided by 6. Now we can write out the partial fraction expansion. A divided by s is 4. B, this is a minus, divided by minus 1, plus c divided by s minus 2. And now we have solved the algebraic problem, and we can use the table of inverse Laplace transform to get us to the original solution of the ODE. The third step is to perform inverse Laplace transform in order to get y of t. So we have constant inverse Laplace using the linearity property, and do it term-wise. And from the Laplace transform table, we can see inverse Laplace transform of 1 divided by s a is e to the negative at. So y of t, using inverse Laplace transform, the first one, a equals to -4, so e to the 4t. Second term, we have a equals to -1, so plus t. The third term, we have e to the a equals to -2, so plus 2t. Now we have solved the solution for the ordinary differential equation. Note that this is the algebraic problem, although it is tedious, but it is far more simpler than solving the general solution and then solve the particular solution, because we have a non-homogeneous term. In conclusion, we have solved ODEs using Laplace transform for first and second order linear equations. And we have seen that this process, although algebraic problem is tedious, it is far simpler than solving the general solution and then solve the particular solution for the original ODE.